Today we'll be talking about the integral. So what is the integral? The integral is the area under the curve. But what does that mean? Well, back in the day before calculus was a thing, and you had a graph, and you wanted to find the area from point A to B, you couldn't. So then someone was like, but what if I could? Or at least get very close to it. Well, we start off with something that we do know the area of, and that of course is a rectangle. And that'll give us a pretty decent approximation when we add up all these areas. So all this, plus all this, plus all this, and all of this. But as you can see here, you actually have a bit of the area above the curve, and that's not exactly ideal. Someone then noticed that if we were to actually make these rectangles smaller, again keeping from A to B, that the actual amount of area above the curve is greatly decreased. And if this is greatly decreased, then the addition of all of these rectangles will give you a better approximation of the area under the curve. And that is where this comes in, or that equation. So as you can see there, we have something that looks awfully familiar, and that is this. We know that the area of a rectangle is equivalent to the base times the height. Well, if you were to get an equation and you plug in f of I of x, whenever you plug in f of x, you're going to get a result y. So if you look at our xy, f of I of x is going to give you y, and that is going to be the height. And now delta x. Delta x is going to be, if you look at a rectangle, let's call that x initial, x final. Delta x is equivalent to x final minus x initial. That's going to give you the base. There's that. So we see that this is the area of the rectangle. But now, as we can see, we have multiple rectangles. So we're going to have a sum. But what's good about this formula is that we have the limit as delta x approaches 0. So as we saw here, we have x final and x initial. That's going to be equivalent to delta x. And as we saw going from this first graph to the second graph, that if you decrease the width of the rectangle, you're going to get a better approximation of the area under the curve. But what if we could decrease the width of the rectangle to pretty much 0, or at least very close to 0, which is what the limit as delta x approaches 0 means? Well, then if you get a rectangle that is so small that it's so close to 0, well then you're actually going to decrease the amount of area that you have above the curve, and that'll give you pretty much as close, if not exact, or as very close as you can to the area under the curve. And that, sir, or ma'am, or whoever's watching, hello, is what the integral is defined as. So now we have this, the integral. The integral from, let's say, a to b of f of x, which is just any function dx, is our integral. So we look at it and we see very familiar things. This is the integral sign. That's not pointing at anything, but now it is. That is the lower limit. This here is the upper limit. This here is the function. And this here is dx. Dx actually will tell you in which direction we're going to be essentially cutting, or which direction is going to be getting smaller. Which direction is changing. That's what the d is. D of x can also be written as delta x. So this just means that, as we saw before, our rectangles, they're getting much, much smaller. and smaller in terms of the base, not the height. The height is just dependent on the function, which is here, and that is the same. That is constant. The only thing we're changing is the base or the width, and as we saw earlier, that's going to give us the best approximation of the area under the curve, otherwise known as the integral. So now let's move on to actually solving them. In order to solve an integral, you follow a few basic steps. Let's say you're just trying to integrate x raised to any power. When you do that, your result is going to be x raised to whatever you had plus 1, and then it's going to be 1 over whatever you got up here. And then if you have limits, it's going to be from the lower limit to the upper limit. Let's do some examples. Integral of x, so you're going to, again, here is a 1 here and a 1 here. You're going to have 1, you're going to add 1 to it. You're going to add essentially the reciprocal, 1 over 1 plus 1. That is going to give you 1 over 2x squared. Now, since you do not have limits here, you're going to add plus c. Moving on to the next example, we're going to do the same thing. It's going to be x2 plus 1. This here is going to be reciprocated and put in the front. It's going to give you that. You're going to then get x cubed, 1/3 x cubed, and then again, plus c. Let's try up another question. Here we have 5x squared. 5 is a constant, so 5 can actually come out. Since it's constant, it's not going to be changing. You're going to get 5 integral of x squared dx. That'll give you 5 times x2 plus 1 over 1 over 2 plus 1. That'll give you 5 times 1/3 x cubed plus c. Moving on to the last one. And now a property of integrals is that you can actually divide them up. So this integral of 5x squared plus 2x dx is also going to be equivalent to the integral of 5x squared dx plus the integral of 2x dx. Again, where dx is also equivalent to delta x, and that, as we remembered from earlier, is what we are taking the limit of as it approaches to 0. There you go. And so, working it out, you do the same steps. Take the constant out. That'll be a 5 times the integral of x squared, which is going to be plus 1. Let's move this over so I have some space. 1 over 2 plus 1 plus, do the integral of this side. It's going to give you, take out the constant, that's 2x plus 1 plus 1, and then 1 over 1 plus 1 plus c. Solving everything out, here this is 1 over 3, that is 3. 5 times 1 over 3 is 5/3 x cubed plus this here is 1/2. 1/2 times 2 is 1. So it'll be plus 1. 1 plus 1 is 2. 1x squared plus c. That is your final answer. As usual, you don't have to include the 1. It could just be 5/3 x cubed plus x squared plus c. Same thing. But what does that all really mean? So let's say we have an integral from a to b of x dx. And let's say here's a and here's b. Well, as we saw earlier, we can actually take apart integrals. And so this actually means it's the integral from 0 to b of x dx minus the integral of 0 to a x dx. But now, what are these? Well, integral from 0 to b, here's 0, here's b. It's going to be the area under the curve from 0 to b. Now, the area under the curve from 0 to a is from here to where a is. That's going to be that. And so if you notice, if we take this whole area from 0 to B minus this area from 0 to A, what you're left with is the area from A to B. And that is what the lower limit and upper limit actually mean. They essentially tell you you're taking the area from the lower limit, which is A, to the upper limit, which is B.